Within the whispering darkness of the universe, there is an unrelenting question that has tugged at our collective imagination for centuries. It is not merely a curiosity about destiny, but a deep yearning to fold our own narrative, to meet ourselves in the past and rewrite the words we once said or left unsaid. The story of time travel teeters on the edge of a cosmic dream and a scientific impossibility. We gaze at the swirl of stars and wonder if somewhere, somehow, the fabric of time is porous, and whether we might slip through a seam into another moment. The very thought is intoxicating. Yet behind the seduction lies a delicate balance of physics, probability, and memory that quietly suggests a different outcome. If you could close your eyes and step onto a roller coaster that carried you back to the day that shaped your life, would you? Or would you fear what might unravel? Listen as the tale unfolds. Welcome to the cosmos and dust. I invite you to subscribe, to settle into your favorite seat, to let your eyelids rest and your breath slow. Let the weight of your day fall away as the night stretches endlessly before you. This is not just a lecture. It is a lullaby woven from equations and stardust. Close your eyes and imagine the velvety darkness of space. Somewhere beyond your walls there are galaxies in motion and tiny particles entangled across unimaginable distances, humming with secrets about the very question that calls to us. Allow yourself to drift along the currents of thought and feel the vastness of what we are about to explore. Our first exploration wanders into the heart of our own perception. We remember the past and dream of the future. We do not remember the future. This asymmetry is not just psychological, it is embedded in the universe. There is a law that describes it, an elegant principle from thermodynamics, the tendency for disorder to grow. The universe began in an extraordinarily ordered state, and since then its disorder has increased. We call this measure of disorder entropy, and its relentless rise is the arrow of time. Every shattered glass that fails to reassemble, every ripple that fades into stillness, is an expression of entropy climbing. In a simplified example, imagine two people watching a film and raising or lowering their thumbs in approval or disapproval. Their possible combinations of approval and disapproval can be described by probabilities. When we calculate the entropy of these states, we see that it increases as we allow for more variability. In the cosmos, the distribution of particles, the vibrations of molecules, and even the patterns of your own memories all follow this rule. The arrow of time is not inherent to the laws of physics themselves, which can run equally forwards or backwards. It emerges from the statistical nature of many tiny parts interacting and from the improbable order of the universe's beginning. As a result, we move from memories of what has been to uncertainty about what will be. Our lives are a procession in one direction, punctuated by the irreversible aging of our bodies and minds. This simple principle, entropy increases, might seem mundane, but its implications for time travel are profound. Consider a clock. A clock needs friction to count its swings and release each second. Friction and wear produce heat, a microscopic scrambling of the clock's internal parts that can never be unscrambled. Because of this dissipation, a clock's entropy must grow with each tick. Now imagine that clock tracing a closed loop through space-time, returning to its starting point. If entropy has increased throughout its journey, there is no way for the clock to end in the exact same state it began. Something must have worn or changed. This is a simple system, but the logic extends to everything like us. Memories, cells, the warmth of our hearts, all depend on processes that cannot run in reverse without leaving behind some signature. Each moment you live burns its own pattern into reality. If you could travel back, you would carry a scar of friction with you. The laws of thermodynamics therefore whisper that a human cannot complete a perfectly closed loop and return unchanged. There is, in this sense, an intrinsic resistance to going backwards with yourself intact. Yet the mathematics of general relativity, Einstein's great theory of space and time, allows for the existence of curves that loop back on themselves. These are called closed, time-like curves, and they are solutions to the equations that describe gravity. In such a universe, a traveler could in principle move forward in time along their own path and end up at an earlier point. To create one, some have imagined traversable wormholes, tunnels connecting distant places and times. If one mouth of a wormhole sits deeper in a gravitational well than the other, time flows differently at each end. Over a great number of orbits, the difference accumulates. A traveler could enter one mouth and emerge before they left. It is a playful mathematical possibility, but there is a problem. Wormholes require exotic matter with negative energy to remain open, and every object we have ever touched has positive energy. This requirement is so bizarre that it prompted Stephen Hawking to propose a chronology protection conjecture, suggesting that the universe forbids the creation of such loops. Even if negative energy exists in the oddities of quantum fields, there is a more fundamental obstruction. When physicists examined the horizon that would surround a closed time-like curve, they found its area would shrink. According to the generalized second law of thermodynamics, the total entropy inside and outside this horizon must not decrease. A shrinking horizon reduces its associated entropy. To compensate, other entropy would need to increase to an impossible extent, an infinite adjustment. As a result, time machines would violate the generalized second law and are deemed impossible. The cosmos defends its arrow of time with more force than we could muster. If you could rewrite one choice in your past, would you? Consider the ripple of outcomes that would follow from that change. Would the person you are now vanish? And if you could travel back but erase your own memory on return, would it still matter? Tell me in the comments. I read each note and wonder at the diverse reflections we share. Our journey now descends into the quantum realm, a place where the rules of probability and uncertainty blur into each other. Here, time is less rigid, and certain processes are reversible. At very small scales, particles can move through various paths simultaneously, interfering with themselves in ways our intuition struggles to grasp. Quantum mechanics has a strange grace. It allows for superposition, entanglement, and delayed choice. Some researchers have used these features to simulate what a form of backwards influence might look like. Two particles that interact can become entangled, meaning their properties are correlated no matter how far apart they drift. An experimenter may entangle two photons, send one to interact with a sample, and keep the other aside. When new information arrives later, they manipulate the held photon to change the probability distribution of the first as though they had adjusted it earlier. This is not actual time travel. No information moves faster than light. Instead, it is a clever way to retroactively improve a measurement. The simulation works sometimes. About 1 out of 4 attempts succeed. In the remaining cases, the experimenter knows the failure and tries again. By sending many entangled pairs, they ensure that some will align with the desired outcome. This method, based on entanglement and filtering, uses quantum mechanics to fix yesterday's problem tomorrow. But it does not break causality. It requires a cascade of trials and a filter to select the rare successes. This probabilistic nature of quantum adjustments hints at something subtle. Quantum mechanics does not outright forbid the smoothing of paradoxes. It allows small fluctuations to adjust histories in self-consistent ways. A remarkable derivation shows that if a system follows a closed, time-like curve at the quantum level, the only consistent histories are those that align perfectly. In such a loop, all processes must complete an exact number of cycles before returning to the start. Energy levels become evenly spaced according to the length of the loop. Vibrations, heartbeats, and pendulums must fit perfectly. Anything that does not fit cannot exist on the loop. Because the system must retrace its steps, there are two directions of increasing entropy. After a certain high entropy point, all thermodynamic processes, including biological ones such as memory formation and aging, run in reverse. The loop contains a lowest entropy event and a highest entropy event. From both directions, entropy rises toward the high point and then falls back, causing the cycle to unwind. If you were in such a loop, you could not keep your memories. When you reach the beginning again, your body and mind would return to their original state. If you had written a note or aged or learned something, these changes would fade. You would end exactly as you began, with no awareness of the journey. The paradoxes vanish because the laws themselves prevent contradiction. Take a moment to breathe this in. When we fantasize about time travel, we often imagine seeing ourselves at different stages, offering guidance or mischief. But quantum mechanics shows that if such loops existed, they would preserve consistency by erasing the possibility of interference. You could not kill your grandfather, because the version of you that attempts it would not be the same version that emerges from the loop. The older person you meet at the start of the loop would be a fluctuation, not a continuation of your life. The self-consistency principle emerges naturally. History must align with itself. The cosmos does not permit contradictory threads. Even rare events predicted by the Poincare recurrence theorem, which states that a finite system eventually returns to earlier states, are choreographed to ensure harmony. The loop might produce a moment that seems spontaneous, a structure or person appearing without ordinary cause, but this arises from the finite set of possible configurations repeating in time. If you could visit yourself 10 years ago but knew every memory of that meeting would be wiped clean by the end, would you still go? Would you whisper encouragement, knowing that neither of you would remember? Share your thoughts in the comments. Your reflections become part of our shared exploration. Beyond the quantum and thermodynamic arguments lies the grand canvas of cosmology. The universe began in a state of low entropy, an extraordinarily smooth arrangement of matter and energy. This is puzzling because high entropy states are far more numerous and thus more probable. Why did the cosmos start off so ordered? Some physicists propose that cosmic inflation, the rapid expansion that smoothed out the early universe, set the initial conditions. Others, like Sean Carroll and Jenny Chen, suggest that empty space with a tiny vacuum energy may spontaneously generate patches of inflation, leading to universes like ours. In either case, the arrow of time flows because the early universe had very low entropy, and entropy has been increasing ever since. As the universe expands, it creates room for disorder. Stars burn, galaxies form and dissolve, black holes grow and evaporate. Each of these processes contributes to the rise of entropy. Even the eventual fate of the cosmos, perhaps a cold and dilute de Sitter space with gentle fluctuations, still contains an arrow. Rare fluctuations can spawn new regions that expand and become universes. Time's arrow might run in different directions in different patches, but locally, within our history, it points from the smooth past to the chaotic future. Our psychological arrow follows this cosmic script. We remember the past because it was more ordered. We anticipate the future because it is more disordered. The expansion of space itself is an arrow of time. As the cosmos grows, structures become less bound, and the tapestry of events stretches. Probability theory plays a silent but central role in all of this. Entropy is deeply connected to probability. It counts the number of ways a system can be arranged while appearing the same at a coarse scale. A low entropy state is special because there are few ways to arrange its constituents. A high entropy state is generic. When we think about time travel, we imagine navigating between these states. But the probability of spontaneously decreasing entropy is astronomically small. In principle, microscopic fluctuations can temporarily reverse entropy in tiny regions, but the chance of a macroscopic reversal is vanishing. That is why we never see the shards of a cup leap into formation to form a pristine vessel. The laws allow it, but the odds are so low that the universe would have to run for times beyond comprehension. When cosmologists talk about Poincaré recurrence, they refer to the fact that given infinite time, a finite system will return to any given state. But infinite time is beyond any human scale. We may as well say, never. Probability builds the arrow of time as much as entropy does. The improbable becomes impossible for all practical purposes. Even when quantum experiments use entanglement to simulate retroactive adjustments, their success is limited by the fundamental probabilities. Only through repeated trials does the desired outcome appear. There is another layer to probability in time, the psychological. When we look back on our lives, we see branching possibilities. In the moment, we choose one path, and the others become stories we tell ourselves. The regret or gratitude we feel is not just about what happened, but about the probability that events could have gone differently. We wonder, if I had spoken up, if I had taken that job, if I had not let fear guide me, would my life be better? This internal replay is a form of mental time travel. It is as close as we come to stepping into the past. It is also shaped by entropic processes in our brain. Memories are not perfect recordings. They are reconstructed each time we recall them. The act of remembering itself changes the memory, slightly increasing the entropy of the neural connections. Our minds cannot return to a past state without some loss or alteration. This is a microcosm of the arrow of time. We cannot help but move forward, even when we dwell on what has been. The philosophical lesson is profound. The arrow of time is not only a physical law, but also a teacher of humility. We can learn from the past, but we cannot relive it without consequence. Imagine the universe as a garden of ever-unfolding petals, each petal a moment. We stroll through, leaving footprints that cannot be erased. There may be loops and paths that seem to fold back, but each is shaped by the constraints of entropy and probability. We cannot tear out a petal and insert it elsewhere without disturbing the whole. Instead of seeking to travel backward physically, we might embrace the idea of traveling inward. We can revisit our past through memory and narrative, draw wisdom from what is behind us, and envision what lies ahead. We can practice compassion for ourselves across time. When we regret, we can ask why we did what we did, given the knowledge we had. When we dream of changing our past, we can instead choose to act differently now. Probability suggests that our future still holds many possible paths. Although we cannot rewrite the past, we can shape the present moment, which in turn becomes a new memory and influences what will unfold. This is a different kind of time travel, a deliberate shaping of trajectories using knowledge of physical law and self-awareness. We have walked through the tangles of theoretical physics and emerged with a deeper appreciation for the universe's commitment to consistency. From the inexorable rise of entropy to the subtle probabilistic dance of quantum fluctuations, from the cosmic expansion to the protective constraints of horizons, time travel as depicted in fiction is rendered improbable by the very fabric of reality. The laws governing friction and heat ensure that systems cannot return perfectly to their earlier states. The generalized second law prevents the creation of closed time-like curves without infinite cost. Quantum mechanics allows for clever simulations and self-consistent histories, but insists on erasing paradoxes by removing memory and reversing processes. Cosmology anchors the arrow of time in the low-entropy birth of the universe and its ongoing expansion, while probability theory underscores the near impossibility of macroscopic reversals. If you could know that your life will unfold exactly as it has, with every joy and every sorrow repeating in perfect detail, would that knowledge bring you comfort or despair? Or tell me in the comments. These questions hold no right or wrong answers. They are invitations to reflect on the bittersweet beauty of being bound to a single direction through time. Your responses create a constellation of human thought that floats alongside the scientific ideas we have explored. As you drift toward sleep, imagine the tapestry of time stretching out like a river. Its current is slow and steady, carrying us onward. The ripples from each action spread and mingle with countless others. We cannot reverse the river, but we can learn to float more gently, to appreciate the reflections on its surface. The impossibility of traveling back does not diminish the wonder of the journey. It enhances it. It reminds us to pay attention, to hold gratitude for fleeting moments, and to act with care. It asks us to weave stories that honor the past while embracing the future. In the quiet darkness, with your eyes closed and your breathing deep, let the certainty of time's arrow comfort you. There is solace in knowing that while we cannot edit our story, we can always turn the page with intention. Sleep well, traveler, and dream not of machines that bend time, but of the infinite possibilities contained within the moment you inhabit. The landscape of time travel theories is as varied as the stars in the night sky. Some models in general relativity suggest that massive, rotating structures might drag space-time into loops. Imagine an entire universe that rotates so uniformly that its angular momentum curls time into a circle. In the mathematics of Kurt Gödel's universe, such rotations create closed time-like curves without requiring exotic matter. Although our universe does not appear to rotate in that way, the thought experiment illuminates the connection between motion and time. Near objects with extreme angular momentum, such as spinning black holes, space-time itself is twisted. Particles, light, and even the passage of time are dragged around the rotation. This phenomenon, called frame dragging, hints at the malleability of time in the presence of gravity. Yet even here, the laws preserve order. You cannot simply spin a region of space fast enough to wrap time back onto itself without paying a price. The energy required would be astronomical, and again, the conditions would create horizons that enforce the second law. At the edges of these gravitational wonders, event horizons create boundaries beyond which information cannot return. A black hole's entropy is proportional to the area of its horizon. When matter falls into a black hole, the horizon grows, and so does the entropy. Hawking showed that black holes radiate, slowly losing mass while emitting particles. This radiation is thermal, meaning it carries away heat. As the black hole shrinks, the total entropy of the black hole plus the emitted radiation still increases. Even the life cycle of a black hole obeys the arrow of time. The story of Hawking radiation is a striking example of quantum mechanics and gravity working together to safeguard thermodynamics. In every case where the horizon shrinks, there must be a compensating increase in other entropy. This is the core of the generalized second law, which forbids time machines. Horizons are not just edges of things, they are keepers of order. The concept of negative energy enters this story through the quantum vacuum. In the Casimir effect, two metal plates placed extremely close together experience an attractive force due to the suppression of quantum fluctuations between them. This region has lower energy than empty space, meaning it effectively has negative energy density relative to the vacuum. It is proof that the quantum vacuum is not inert but teeming with fluctuations. Could this negative energy hold a wormhole open? In theory, perhaps. But the amount generated by the Casimir effect is minuscule and dissipates quickly. To support a macroscopic wormhole large enough for a person, one would need a vast amount of negative energy distributed in a stable configuration. Our best experiments and observations have yet to find such reservoirs. The laws that limit energy densities and fluxes, known as quantum energy inequalities, place strict bounds on how much negative energy can exist and for how long. These inequalities further constrain exotic constructs. They quietly reinforce the chronology protection conjecture by making it extremely difficult, if not impossible, to engineer the required conditions. Another alluring idea from general relativity is the cosmic string, a hypothetical one-dimensional defect in spacetime. If two cosmic strings were to pass each other at high speeds, the spacetime around them might twist into a closed time-like curve. The mathematics is elegant, but the physical reality remains uncertain. Even if cosmic strings exist, arranging them in just the right configuration with the right velocity to create a time loop would be beyond our capabilities. Once again, the interplay of energy, motion, and geometry conspires to preserve the arrow of time. Time dilation, a real and measured effect, also arises from relativity. Astronauts on the International Space Station age ever so slightly less than those on Earth because they move faster and are in a weaker gravitational field. Clocks on GPS satellites are adjusted to account for both their speed and the difference in gravitational potential. These corrections are essential for the accuracy of navigation signals. Such time dilation shows that time is not absolute. It depends on velocity and gravity. But this dilation is symmetric. You cannot use it to go back. You can only stretch time relative to another observer. It allows for forward time travel. Travelers who move at near light speeds age less than those they leave behind, but not return. This one-way elasticity of time is a real, physical manifestation of relativity that still respects the monotonicity of entropy. While relativity manipulates the geometry of spacetime, quantum mechanics explores the fabric at the smallest scales. Superposition allows a system to exist in multiple states at once. Only when you measure it do you obtain a specific outcome, and the probabilities of different outcomes are given by the wave function. In a simple two-slit experiment, a single electron passes through two slits simultaneously, interfering with itself to create a pattern on a screen. If you try to determine which slit it went through, the interference disappears. Such experiments challenge our classical notions of cause and effect. Yet despite their strangeness, quantum processes obey unitarity, an evolution that preserves the total probability. Even when entangled particles are measured at great distances, no information travels faster than light. The correlations are established at the moment of entanglement creation. When researchers use entanglement to simulate the correction of a past state, they do so within the strict confines of quantum rules. The non-local correlations allow them to post-select the outcomes that match the desired history. But this is not free. They must discard the majority of trials. Probability theory underpins this process, weighting the possible histories. Only by accepting the constraint that some outcomes are unreachable does the self-consistent loop maintain coherence. There is a related concept known as the many worlds interpretation. It suggests that every possible outcome of a quantum event occurs in its own branch of the universe. In this view, there is no need for history to modify itself. All histories exist simultaneously but do not interact. Time travel in this context might mean moving between branches, yet there is no known mechanism to jump from one branch to another. The branches are non-interacting by definition. The many worlds picture illustrates the richness of quantum possibilities without offering a route to change our past. It invites us to ponder the multiplicity of outcomes and the intimate link between probability and reality, while leaving the arrow of time intact within each branch. Memory formation and recall are also subject to quantum and thermodynamic principles. Neurons fire and strengthen their connections through chemical processes that rely on energy gradients and dissipative cycles. Each memory leaves a physical trace, a pattern of synapses. Creating these patterns consumes energy and increases entropy. When we recall a memory, we reactivate and slightly alter those connections, subtly changing the memory itself. This means that revisiting a memory is akin to traveling back in time with the cost of altering the past. It is never the same memory twice. The arrow of time thus permeates our minds. We cannot preserve a moment untouched, because the act of recalling it changes its probability distribution, just as measuring a quantum system alters its state. This is a gentle reminder that we are part of the physical world we study. Our thoughts obey the same rules. Our desire to step outside those rules, to loop back and edit, may be as much about our yearning for control as it is about curiosity. From a philosophical perspective, the impossibility of time travel as traditionally imagined might seem disappointing. But there is a quiet liberation in understanding why it cannot be. If we cannot go back to change our mistakes, then regret becomes a teacher rather than a tormentor. Knowing that the past is fixed allows us to focus on the choices we make now. Time travel fantasies often reveal a deeper desire to perfect our lives, to smooth out pain, to correct tragedies. Yet our growth emerges from confronting these imperfections. Each misstep contributes to who we are. Without them, we would be different, perhaps unrecognizable. The impossibility of editing the past ensures that the tapestry of human experience retains its authenticity. There is no alternate path waiting to be discovered. There is only this path, with all its thorns and blossoms. The interplay of determinism and randomness also shapes our perception of time. At the macroscopic level, the laws of physics may lead to predictable outcomes. A planet in orbit follows a path determined by gravity. But at the microscopic level, quantum events are probabilistic. The decay of a radioactive nucleus happens randomly, though with a predictable half-life. These random events can cascade into macroscopic effects, especially in chaotic systems where tiny variations grow exponentially. The weather, for instance, is famously sensitive to initial conditions. The so-called butterfly effect suggests that a butterfly flapping its wings could influence the path of a hurricane. While this is an exaggeration, it highlights that small uncertainties can propagate. Because we cannot know all initial conditions with perfect precision, the future remains unpredictable. Time travel stories sometimes imagine going back and stepping on a butterfly, thus altering the future. In reality, unpredictability stems from the inherent probabilities in the physical world. There is no single strand to cut or tie that will change everything. There is a web of interactions and random fluctuations. Another dimension of time emerges in complex systems: emergence. When many simple parts interact, new behaviors can arise that are not evident from the parts alone. Consciousness, weather patterns, economic cycles, and ecosystems are examples. Emergent phenomena have their own effective laws, which can include their own arrows of time. For instance, the evolution of species under natural selection is directional, as is the development of a human embryo. These arrows arise not from fundamental physics, but from the way systems organize and dissipate energy. Understanding these emergent arrows helps us appreciate that time travel, even if possible at some level, would have cascading effects on these complex processes. Changing one gene in a distant ancestor might ripple through an ecosystem in unpredictable ways. The further we move from fundamental laws into the realm of life and mind, the more intricate the web becomes. Each additional layer of complexity adds inertia to time's direction. The moral and ethical implications of time travel also invite contemplation. If it were possible to travel back and alter history, who would decide which changes are acceptable? Would anyone have the wisdom to adjust events without unintended consequences? Many time travel stories revolve around the consequences of meddling: wars avoided at the cost of different tragedies, cures found but new diseases arising. These narratives underscore that reality is interconnected. There are trade-offs we cannot foresee. The impossibility of time travel spares us the burden of that responsibility. It keeps the moral weight of history distributed across those who lived it, rather than concentrated in a single traveler's hands. It invites us to focus on repairing injustices in the present, rather than wishing them away in the past. Cosmologists sometimes wonder whether time had a beginning. The Big Bang is often described as the starting point, but some models propose a bounce, a collapse followed by an expansion. In bouncing cosmologies, time could stretch infinitely backward, with the universe oscillating between contraction and expansion. Interestingly, the arrow of time could reverse during a contraction phase. Entropy might decrease if the cosmos were squeezed back to a smooth state, yet such theories must still reconcile with the generalized second law and quantum mechanics. Even if time extends without a singular beginning, it remains segmented into phases where arrows may differ. Observers within any given phase would still perceive a forward direction tied to the growth of disorder. The existence of multiple arrows across cosmic epochs enriches the tapestry without granting us the ability to cross them at will. One might ask, is there anything that genuinely moves backwards in time? Certain mathematical equations are time reversal symmetric. If you reverse the velocities of all particles in a simulation, the system will evolve back to its initial state. In a frictionless world with perfect knowledge of all variables, you could, in principle, reverse time. But our world is not frictionless, and we cannot know every variable. The slightest perturbation grows, preventing precise reversal. In superfluid helium or other exotic systems, researchers have approximated time reversal for short durations by carefully manipulating waves or spins. These experiments are fascinating, but they involve controlled, microscopic arrangements and still do not allow causal paradoxes. They demonstrate the subtlety of time symmetry, but reaffirm the arrow's dominance at larger scales. Finally, there's the contemplative question of what time itself is. In physics, time is a dimension like space, but with a different sign in the equations. In our experience, time is a flow. Is time fundamental, or does it emerge from deeper processes? Some theories of quantum gravity suggest that time might emerge from entanglement patterns or thermodynamic relations, that space and time are not basic but derived. If this is true, then asking to travel through time is like asking to rearrange the waves on the surface of a deep ocean without touching the water beneath. The waves cannot decide their own pattern. They arise from the interplay of deeper currents. Our desire to move through time may be limited by the fact that time is not an independent fabric, but a property of the universe as a whole. If time is emergent, then controlling it requires controlling everything. As your thoughts drift like constellations across your mind, notice how the idea of time travel has unfolded here, not as a singular answer, but as a collection of interwoven themes. We have brushed against relativity's malleable spacetime, quantum mechanics' probabilistic loops, thermodynamics' relentless arrow, cosmology's initial conditions, probability's subtle hand, and philosophy's reflections on regret, ethics, and emergence. Each thread supports the others, forming a tapestry that resists being torn. The result is not a definitive no to time travel, but a gentle, reasoned suggestion that the universe values continuity over revision. It allows us to explore possibilities in imagination and mathematics, to simulate corrections in the laboratory, but it protects the integrity of experience. This understanding does not diminish the wonder of our universe, it enhances it. Knowing that each moment is unrepeatable gives it weight. Knowing that the past cannot be altered frees us to accept it. Knowing that the future is open within the constraints of physical law inspires us to make choices that align with our values. Time travel as fiction can still delight and provoke thought, but time as reality is even more miraculous. It is the stage on which every life unfolds, the canvas for every story, the rhythm that connects us to stars and atoms alike. There is poetry in its irrevocability, and there is peace in trusting its direction. As you settle into the stillness of sleep, let this peace wash over you. The night outside holds countless stars, each with its own history and potential. You, too, are a star in a human form, burning brightly for a moment in the vastness. There's no need to travel backward when the present is rich and the future invites you forward. Feel the comfort in knowing that while you cannot step backward through time, you can step inward, exploring your own memories and emotions with newfound compassion. Let the gentle weight of this knowledge soothe you like the hum of a distant star, and may your dreams tonight be filled with wonder.